Good afternoon, everybody. Welcome to SIBGRAPI. So this is technical section 4, graphics and visualization. My name is Claudio Jung from URGS. I'm going to be the chair of this session. So we have 4 very interesting papers in this session. The first one is regularized Kelvin-Lett inversion for real-time image deformation and video time warping. The second one is online frame-to-model pipeline to 3D reconstruction with depth cameras using RGBD information. The third one is visual analysis of forecasts of football match scores. And the last one is Mirante, a visualization tool for analyzing urban crimes. So for each paper, we're going to play back the 5-minute video that each author produced. And then we're going to have an extra 5 minutes for questions and answers. So please post your questions through Wova and YouTube. So first, I'm going to try to read the question posted in the Wova platform and then on YouTube. And please try to post your questions as soon as you have them, because sometimes there is a lag between posting the question and having them available here. Okay? So we are ready to start with the first paper. The presenter is going to be Guilherme Hettinger. So let's start.
We present a new approach for real-time Kelvin-based image deformation and video time warping. There are numerous applications to image deformation and video time warping. From photo editing to video compositing, these solutions are very relevant to the creative industry. Our contributions are an extension of the Kelvin deformation field to inverse warping that uses elastic properties to preserve smoothness and volume, a real-time warping algorithm for both images and videos that has intuitive mathematical basis and implementation, and a simple per-pixel parallel GPU implementation for which the results can be easily anti-aliased and mitigate artifact generation. Our paper also discusses issues such as temporal aliasing on digital videos. The Kelvin equations take into account 2 main variables, the Poisson ratio proportional to the elasticity, and the brush size, which intuitively is the size of the deformation influence. We can see these properties on the video to the right. These parameters are then input for an equation Kp, which calculates the warping displacement for a point P. Here, we have a forward deformation example, where we take a point P and transform it into point Q in the output space. We do that by computing T, which is the sum between the point P and the dislocation Kp. The inverse transformation occurs when we calculate for a point Q in the output space a point P in the input space that would map to it if transformed by T. We represent this by the following arrow containing T to the minus 1. The reason we do this is because it does not require us to fill the possible gaps between pixels in the forward mapped output. This leads to faster computation and much higher quality of the output. We have a problem, however. The function Kp is nonlinear, meaning that its inverse does not have a trivial solution, which is why we use the Gauss-Newton method to find the inverse. This algorithm can be executed independently and in parallel for all pixels Q in the output image space. Please refer to our paper for more details. There are some important details we should go over. The transformation can dislocate and break boundaries. There's also aliasing and the possibility that the transformation is non-invertible. As we deform the 2D space and the 3D space, it is natural that the edge pixels of the image or video are deformed as well. This unfortunately leads to undesired border artifacts, such as the one around the grid shown here. To mitigate this, we use a controller function on the deformation, which slows down the warping process around the edges. Pixel displacement can lead to aliasing, much like in this example. We can use anisotropic filtering by using a mipmap pyramid. We can derive the mipmap level of our given pixel from the deformation's gradient. Once we do this, we have a clean anti-alias result. There's a possibility that the volume folds over itself when the warping is too strong, creating a non-invertible field. We show how to detect and mitigate this in our paper. We implemented our method on the CPU using Julia, which we use for computing the image deformation examples. This implementation is very efficient and easily parallelizable. We also implemented our technique on GPU using OpenGL, which we use for high efficiency video time warping. The Gauss-Newton inversion was implemented on the fragment shader. and we achieved an efficiency of 300 frames per second on a Full HD 1080p video. Here, we see the results of the Krita's image editing software deformation compared to ours. Different from our result, Krita's results do not preserve volume and contain edge discontinuities and aliasing. Here, we show how the inverse deformation has more precision when computing the output pixels. We can prove so by showing the results on a fractal image. Our result trumps the forward mapped output deformation as it generates clean and precise results, while the other produces blurred fragments generated from the post-deformation interpolation. Here, we exemplify a simple transition on the video time warp can generate. The input is an instantaneous transition of colors, and the output is a smooth circular transition. In this example, our goal is to slow down the zoom out movement centered on the flower. We do so by using our technique, resulting in the video to the right, where the flower only zooms out smoothly around the end. In this other example, our goal was to stop the water from filling the center of the cup for a longer time. In the result, we see that the cup is filled to the top before filling its center. In conclusion, we presented an extension of the Kelvin deformation field to inverse warping, a real-time warping algorithm for both images and videos that has a simple per pixel GPU implementation and generates smooth, high-quality deformations. We proposed a fixed boundary extension of the Kelvin field. We showed how to the deformation gradient, use the deformations gradient for anti-aliasing. We show how to detect and handle non-invertible fields, and in our paper we discussed issues such as temporal aliasing on digital videos. We would like to thank our sponsors and everyone that helped us with our work. Thank you so much for your attention.
Thank you, Guilherme. I'm gonna check WOVA to see if you have it.
Hi, good afternoon.
Oh. Okay, so please post your questions through WOVA. I'm not sure if I'm checking the correct site here. On YouTube. Let's see. Okay, so I do have a first question. You said in the paper you show details on how to deal with temporal consistency, right?
Yeah.
Can you just briefly guide us through this process?
Okay, so the idea is that videos, we can't perceive videos with temporal discontinuities when we consider frame by frame scenarios. When we watch an image stream, the video can seem continuous, while when we try to blend frames together, they create spatial discontinuities. And this idea is one of the limitations of our paper, where we have to consider high frame rate videos or videos in slow motion that have and thrive on frame continuity, right? So in our extended presentation, we still have some examples on how this temporal aliasing can transform itself into spatial aliasing when we try to deform the video.
Okay, and another question is, have you tried to use this deformation field for image or video retargeting? I mean, there are several approaches for retargeting that use these deformation fields to kind of erase parts of the image or the video that are not important.
No, we didn't. Since this idea was only to experience how it would be to change the time step of the frames inside a video, and to see if we could deal with some retiming of pixels and stuff like that. We try to concentrate ourselves in being able to achieve that in a high efficiency scenario.
Okay, we have a question from James Gain here. Thanks for the talk. Is there any way of making the Kelvin-let function homeomorphic so that you don't have to do and detect and post-process the correction scheme?
Okay, so You mean I don't think there is. So the calculate equation is really complex, and we took it out from another paper by the Ghost. So we don't necessarily have the knowledge we would like to have on the calculate equations, but the calculate deformation is actually something that has already been here for a long time, and it's the idea of elastic deformation, right? And what I can say about this question is that we use inverse warping not only to correct that idea of post-processing on a forward image output, but because it's faster, and it can also be used on fractal images. I don't know if that answers exactly your question,
Please,
but
James, if it doesn't, let us know here.
yeah.
Thank you. And another question from Joaquim Bento. And what happens if there is no inverse? What do you do then?
All right. So this is some of the topics on our paper, which is the idea of detecting non-invertible fields, right? So this scenario that Joaquin is pointing out is the idea that we can map we can map one output pixel into two input pixels, right? And because of that, we would have a fold over on the deformation process, and this would lead to a non-invertible field, right? We showed how to detect that and mitigate it on our paper. It's kind of complex to explain it here because it has a lot of mathematical background. But if you just read it, it would be explained on the paper.
Right. So let me just check Bova to see if there is anything there. Oh, okay, the same question. All right. So I think maybe we have finished the 5 minutes dedicated for questions. Thank you very much for the presentation and all this discussion after the presentation,
Yeah.
Guilherme.
Thanks for your time.
Okay, thank you. So let's move to the next paper. The next paper is online frame to model pipeline to 3D reconstruction with depth cameras using RGBD information.
Hello, my name is Thiago, and I'm going to present you this work, which is an online frame-to-model pipeline to 3D reconstruction with depth cameras using RGBD information. This work was done at Institute of Informatics at Federal University of Rio Grande do Sul. The goal is to develop a pipeline for processing sequences of RGBD images in order to reconstruct 3D models using RGBD cameras of near range like Kinect. We propose a 3D reconstruction pipeline for this temporarily continuous RGBD data suited for near range sensors. The core of our approach is to take advantage of the geometric alignment when there is low color information and explore color matching when we compensate for the low geometric information in locally plotted regions. As contributions of this work, we first implement a pipeline that works online, being capable to do reconstructions with low drift estimates. Second, we proposed a PNP solution in order to initialize the camera position. And finally, we propose a weighting scheme in order to avoid the influence of bad depth data in the final result. That one is important because in this context, errors in the line of depth and RGB images may lead to estimation of erroneous correspondences, especially in the regions of discontinuity or with a wide inclination concerning the camera axis. Trying to avoid these problems, we use a weighted correspondence scheme that considers normal map information to choose which point correspondences are reliable to the alignment process. Taking a look to the previous works, we have observed some space for improvements. Kinect Fusion and the NSP uses only depth data. This results in instance of more limited convergency. Open3D does not consider the noise of depth data and the RGBD camera calibration errors when registering RGBD and depth sensors. As shown in the work of Silveira and Jung, using features that are spatially spread tend to produce more accurate results in the context of a people or matrix estimation. So working with near-range data is more challenging to avoid bad registration. Trying to address these problems, now we propose a pipeline to deal with it. This is an overview of the pipeline. First, we filter the depth and color images. Then, we get the normal map and a weight map based on the filter depth image. We find the initial pose using EPNP algorithm and the orb features. And after that, we find the final pose by minimizing an error function that considers the weight map obtained before. The new depth data is integrated into a reference model, and we project the reference model and generate a depth image that's used to align with the new depth images. And that's it. We wait for contact and follow emails. Thanks.
Sorry, the mic was mute. Let me check Wova first. So no question there. Let me check YouTube for questions. Okay, so there is actually one question by Soraya. Can you talk a little bit about computational cost? And is it real time? If it's not, how can you improve it?
Hello, people. Thiago here. This computational costs is, I think, is the main cost of this algorithm is the Gauss-Newton at when minimizing the function. And I don't think it's possible to build a real time algorithm as it works per pixel basis. I think it's plausible, but in our implementation, it was programmed in CPU, so it don't works at real time rates. But I think it's possible to construct something like that.
Okay, let me just add to that question. And so you didn't do any kind of GPU implementation, and if not, is it possible?
I think it's possible. I think it is at least plausible to do something like.
Check over again. We are here. So, any more questions from the audience about the paper? Well, and thank you, Thiago. Thank you for the presentation. Thank you for the answers.
Thanks, Claudio.
So let's move to the next presentation. Oh, where? Can you pause it a little bit, Thiago? So it seems that one final question just appeared here. Can you put Thiago back on? Oh, okay. Okay, Gastão, it seems that Thiago's not here anymore. Thank you. Let's go on to the next presentation then.
Hi everyone, we are from Fundação Getúlio Vargas in Rio de Janeiro and are here to present our paper, Visual Analysis of Forecasts of Football Match Scores. We use visualization techniques to help evaluating the performance of a forecasting model for football match scores. Our model uses independent Poisson random variables to simulate the number of goals scored by both teams in a football match. We combine an attack parameter for one team to a defense parameter from the opposing team, and then use the Poisson distribution to generate the probability for each score. Then, when we have the actual score of the match, how can we say if the prediction, if the forecast was good or not? We have to define some evaluators to do that. We work in 3 different approaches. And in the end, we have 4 evaluators and 4 visual tools to help analyzing the performance. The first one is the actual score position in forecast ranking. Each match forecast receives a grade from 0 to 10. Second one is the probability forecasted to the actual score. Each forecast receives the probability predicted to the score that actually happened. The third one is the actual score distance to probability distribution, or the error relative to some distribution represented, like the mean of the distribution. We can use the mode of the distribution as it's represented and take the error to the mode. And that's our 4 evaluators. We went on to seek if the model will have the same accuracy for all 20 teams in the league. We calculated the evaluators for the matches of each specific team and plotted them into a chart. And in the end, we feel we accomplished our goal, and we're satisfied with the metrics and visualizations presented in this paper. And that's it. Thanks for all, and we'll now take a quick look at the charts, the interactive charts. You can see the probability assigned to each forecast, the errors, you can filter by fixture, this particular one, and compare the regions of the 2 targets. They are different. And finally, the evaluators for each team. And that's it. Thanks again.
So thank you for the presentation, Flavio. I'm gonna check. Oh, so I'm gonna check for questions first in Wova and then YouTube. So while people are thinking about their questions, I have a few actually. So one of them is how do you evaluate how well a forecast is? I mean, you have a winning team, maybe you have a tie, a losing team, and plus the score, right?
Mm-hmm.
So how exactly do you quantify how good a given forecast is given the actual result?
Yeah, that's the purpose of the work. There's no single way to do that. You have to define one or a set of metrics to assess the goodness of the the forecast. The first one would be it's the top predicted score. Did it happen or not? It's the simple one. But when you are probability forecasting, you have a probability for each score, and sometimes the top rated, the top predicted score has 10% of happening. Means it has 90% of not happening. So it's not an easy task. So we define 4 evaluators, and maybe we can have more in order to do so.
Okay, and in the end, you said that you have analysis for each team, right? So
Yeah.
for some teams, I guess you maybe the forecasts are better than for the others, right?
Yes.
Do you have any clue? I mean, teams that are in the top in top scoring positions, usually they win a lot, so you predict that they win, and you make better forecasts. Is that correct? I
Yeah.
mean, is there any correlation?
We found out that the teams had very different performance. We tried to detect if it was the ranking and the final championship points or another thing. If we were forecasting just the result, winning or draw, probably we'll have for example, Flamengo had 90 points at the end of the championship.
Last year, not this year.
But we're not forecasting the results, but the scores. So
Yeah.
it was really difficult to find the final score for Flamengo match, for example. When we had that picture, the worst one was Goiás, and Flamengo, I think, was the second or third worst predicted. Because we tried to discover why, and we concluded that the more goals the matches had, the worse the predictions were in average, because the low score matches had higher prediction probability in general. Not
Actually, I
always,
think
but in general.
oh, sorry to interrupt you. There is another related question by José Florencio Neto. Why did you choose the Poisson distribution?
It has been observed back in the 60s or 70s that the scores in football, if you pick a set of football matches and you distributed the goal score by a team, it follows close to a Poisson distribution. So since the first models, I think first one I think is from Maher in 1982, he was using Poisson distribution back then, and I think to model the score, it's still the most used way until now, up to date. Not necessarily independent Poisson, but Poissons, bivariate Poissons, and so on.
Okay. Thank you for the answer. Let me check if we have more questions. And if not, I have a final one. So did you try your visualization tool for other leagues rather than the Brazilian Championship?
No, not yet. It's in the work to do. We need to analyze other championships, and we'd like to have other models too, so we can compare, because the visualizations, we can see between the matches what were the best forecasts, but we can't conclude if the model was good or not in the end, because we have only one model. So the work to do is to run other models in the same championships and run it in other championships to see the difference, if some championships are more predictable than others.
Yeah, because in Brazil, it's very hard to predict who's going to be the champion, at least in other leagues. If you go to Spain, it's... Okay, and one final question, again by José Florencio. Have you applied the Poisson distribution independently to each team?
Yeah, the model uses independent Poisson, though it's, how can I say, you don't think, I don't think anyone think it's really independent. Once a team score a goal, sometimes or most of the times the match changes. The team who was attacking starts to defend and things like that. But when analyzing the results in general, it's not statistically significant that the independence cannot model the... So it's easier, and it works, or at least works when compared to another models. You don't lose much by using independent Poissons.
Flavio, thank you very much for the answers.
Thank you.
I think we are ready to move to the final paper. Mirante, a visualization tool for analyzing urban crimes, by Germán Garcia.
Studying crime patterns in big cities is a challenging problem because they typically present large spatial areas, great variability of patterns, and a high volume of crimes ranging from petty thefts to homicides. Many countries in the world had a dramatic rise in the criminality of different types. Analyze crime patterns is a crucial activity to prevent, control, and reduce the criminality in a region. In this context, visualization tools have proven to be critical in helping crime analysis. In this work, we present Mirante, an effective crime mapping visualization tool that allows the analysis of spatial temporal crime patterns in a street-level scale. This system has been designed in close collaboration with domain experts as a scalable and versatile tool that could be implemented in any city. Our approach made up street-level heat maps based on the density of crimes for each street segment. For that, first, we modeled our region as a street network considering as a node the street's intersections. Second, each crime event is approximated to the nearest node, computing the crime density of a node. Third, street-level heat maps construction based on the density of crimes. Mirante does not use only Euclidean distance. Instead, it implements an H-node strategy to improve the visualization. Our system is composed by 7 components detailed in the presentation video. Mirante's capabilities are highlighted by 2 case studies. Both of them were addressed in close collaboration with domain experts from 2 cities in Brazil, Sao Paulo and São Carlos. São Paulo is one of the largest cities in the world and the most populous city in Brazil, with around 12 million inhabitants. On the other hand, São Carlos is a city in the interior of the state of São Paulo, and it hosts a variety of academic programs and companies linked to the technology. The first case study analyzes the pattern of vehicular robbery in a region of São Paulo city. The main task is to understand the impacts according to the changes in the local infrastructure. To perform this case study, we selected a region in the south part of the city. It is located near a favela. Alerted by many complaints about vehicle robbery in that zone, we focus our study on this type of crime. Looking to exploring the street-level heat map view, it could be noted 2 red spots, A and B. Using temporal evolution view for a temporal filter, until November of 2010, the node with the highest concentration of criminal record were located in A. However, over the time, the number of occurrences was reduced at A, and the highest concentration of crimes moved to B. So, is there any explanation for this change? We use Google Street View to figure out the reasons. Looking at photos from A and B until 2011, notice the parking area is in A and not in B. Nevertheless, when we look at the photos from 2011, it's evident a change in horizontal signage in A and the implementation of a parking area in B. Thus, the results suggest a risk of burglary was linked to the streets with more potential usage of parking areas. In the second case study, domain experts were interested in knowing whether the recent improvements in the infrastructure have any effect on the criminality of a principal avenue that has a viaduct, a well-known criminal attractor point. For this analysis, we considered the passerby robbery in a selected region. The analysis was divided into 3 years. In each one, we have analyzed the behavior of criminality considering the most prevalent period of the day and how is their evolution over the years. In 2015, notice that the crimes occur most frequently in the afternoon. There are no people living under the viaduct, but during the afternoons, the viaduct became a point of meetings of a group of marginalized people, which can explain why robberies increased in that period of the day. In 2017, the crimes occurred most frequently at night. In this case, homeless people are living under the viaduct. Domain experts attribute the increase of the number of crimes in that period of the day. During the final part of 2018 and the first quarter of 2019, there is a significant drop in crime under the viaduct. At the same time, there is an improvement in the physical infrastructure. According to domain expert, the recent improvements in the infrastructure of the viaduct can explain the decrease of the number of crimes.
Thank you for the presentation, Chairman. So let me check first Ruva and then YouTube for questions. I would just ask the audience to type the questions as soon as you have them, because there is a lag to see them here in the system. But I do actually have one question. So in your final analysis, you evaluate a viaduct, right?
Yeah.
So probably crimes are under the viaduct, but as far as I understood, you register all the crimes at the intersection of the streets, right?
Yeah.
So in theory, you don't have any crime exactly in that location, right? You have probably in a nearby corner. Is that correct? How did you? I mean, how did you conclude that you have a crime situation under the viaduct if that's not a corner in your graph? It's not an edge in your graph.
Actually, we worked with the geolocalization of crime events, and we approximate to the nearest node. In this case, the viaduct is a node, and we approximated the criminality around the node to this node. And after that, we validate some hypotheses of the public security authorities. And one of the hypotheses is that public infrastructure or the improvement in public infrastructure affect directly the criminality in a localization. So we validate that with temporal photos. We extracted photos from 2011, 2017, and we validate that hypothesis we validate the hypothesis of the direct influence of the infrastructure.
A question from José Florencio here. How do you calculate the hotspot?
In this case, in this version of Mirante, we are not worried about the hotspots. In our case, in the system, the hotspot could be considered as the red point. And in our future versions of another system that we are working with, we are considering different mathematical and computational mechanisms to calculate the hotspot in a street level of detail.
Okay. I'm going to keep checking on the questions here, but I have another one. You have data from the probably police reports, right?
Yeah.
And they are given as addresses. Is that correct? Do you look kind of parse the addresses, or do you have GPS locations?
Yeah, we have geolocalization, latitude and longitude of a crime event.
Okay. So you don't have an actual address. You have the geolocalization, and then you can map to a position in the map, and then you approximate to the nearest corner in the graph, right?
Yeah.
Okay. And another question probably is related to mine is, do you approximate all incidents to the corners?
Yeah. We approximate all incident to the nearest corner.
Okay, so if it's, I'm going to add to the question, if the crime is exactly in the middle of a block, then, well, probably sometimes you might push it to one corner and sometimes to the other, right?
Yeah, actually, we first approximate to the nearest edge, and after that,
Okay.
to the nearest node.
Okay, but if it's exactly in the middle of the edge, like in kind of in the same distance from the corners,
Okay.
and sometimes maybe you can push it to one corner and sometimes to the other one, right?
Yeah, that's right.
Okay. Did you notice any kind of effect that it's probably it's not an issue, but
Yeah, I didn't know. I didn't notice that.
okay. So on our question here, did you use open government data? How many events do you have in total? Like what's the order of magnitude?
Okay, we have worked with two cities in Brazil. We have worked with the city of Sao Paulo City and Sao Carlos City. In Sao Paulo, we have been working with the Center of Study of the Violence, so it is not open data, and we have around 1 million incidents. And in Sao Carlos, we have almost 1 million of incidents too, but it's not open data.
In which time period?
In Sao Paulo, it's from 2006 to 2017, and in Sao Carlos is 2014 to 2019, I think.
Okay. And are those events like evenly distributed in time? So maybe there is more report now than like 5 years ago or 3 years ago. So how does that affect your analysis? Because maybe you have more crimes now because they are just being reported more often now, not exactly that they are more often now.
It is an interesting thing to be considered in the future. We didn't consider it in this analysis, but it could be affect directly the analysis.
Okay, I'm gonna check WoW again, and let's hope that there isn't any question that has not appeared here. But thank you very much for the presentation and the answers, Herman. And actually, I'd like to thank all the presenters and the audience. So we are actually 10 seconds from the estimated time. I thank you all for attending SIBGRAPI, and I hope you can attend to other sessions and the invited talks. So thank you very much, everybody. Enjoy the conference. Bye-bye.